Hello everyone, and welcome back to AP Calculus. The focus for today's lesson will be one-sided limits and the definition of continuity. As you completed the lesson preview, I hope that you recognized that there were many details that you needed to consider. For example, in question B, you have a closed interval starting at -6. And then you go to the open interval 4, use the union symbol to connect from -4 to 8, and 8 once again has the close symbol. So keep an eye on the little details such as those. And for question C, where does your function g of the limit fail to exist? That's going to be equal to x equals 1. And your discontinuities is a new definition perhaps. So if you would like to reconsider your answer after we complete the lesson, that's probably a good idea. Now we're looking at question E. Your domain is closed interval from -1 to 1, but the limit will not exist at -1 because the limit from the left does not equal the limit from the right. And when you write those details, make certain you are using the correct notation. The limit as x approaches -1 from the left of f of x is not equal to the limit as x approaches -1 from the right. There's no way that they could be equal because the left limit does not. There is no part of the function on the left side. So where does your limit exist? We're going to use open interval from -1 to 1. So our first three examples are going to be talking about discontinuities and what they might look like. So for example 1, we have f of c is undefined, and we can see that because there is a hole in the graph. So when you think about the domain of this graph, you would write A to C, do not include the C, union C to B when we're using interval notation. Notice A and B are also not included in your domain. When we think about example 2, the limit as x approaches c does not exist for either of these examples. Now the first one, it doesn't exist because there is a jump. And when there's a jump, we call that a jump discontinuity. The second one in example 2 also has a problem at c. The limit does not exist there. This is a vertical asymptote. So for our third example, as we look at the discontinuities, you can see once again that we have a hole at x equals c. But the limit does exist at c. Matter of fact, the limit as x approaches c from the left of f of x does equal the limit as x approaches c from the right of f of x, but it does not equal the function evaluated at c. And because they are not equal, this is called a removable discontinuity when your limit exists, but the value at f of x does not exist, or it's not equal. So we take these three ideas, and let's start classifying some ideas a little bit more. You have two examples with removable discontinuities. So example 1 and example 3 have removable discontinuities. Now, as you look at these examples, what we should think about will be our limit notation. First of all, you notice that there are holes. And when you have holes, ideally, they can be plugged in. And you recognize a hole using the limit notation because the limit as x approaches c from the right of your function does equal the limit as x approaches c from the left of your function, but it does not equal the function evaluated at c. For example 1, it didn't equal the function at c because the function didn't exist at c. In example 2, the function did exist, but the c value was jumped down. Some places where this might occur, if you have the limit as x approaches 1 for x squared minus 1 over x minus 1. You know that you could factor this function because you have your difference of squares, and you get your x minus 1 times x plus 1, and look at what happens to the factor x minus 1. You can cancel it out. You remove the discontinuity. And when you remove that discontinuity, you're left with the limit as x goes to 1, x plus 1. Now we substitute in the value for 1 and x, and our limit is 2. So when you first start out substituting, you notice you get a 0 over 0, because of course you're an awesome student and you did that first. Another place where we're going to see this, once that you just practiced recently, the limit as theta goes to 0 for sine of theta over theta. Now you know the answer is 1, but if you take the limit as you approach from the left and the limit as you approach from the right, you get your 1. But these limits do not equal the value. The limit of the sine of theta over theta does not equal the sine of 0 over 0. And because they're not equal, this is a removable discontinuity. Now your non-removable discontinuities, they're a little bit more serious problems going on. So those occur when the limit as x approaches c from the left of your function does not equal the limit as x approaches c from the right of your function. Examples for this might occur. You might have a limit as x goes to pi over 2 for the tangent of x. When you try substitution, you get sine over cosine, and when you get something like 1 over 0. So if you get 1 over 0 or any number over 0, you should recognize from your pre-calc days that you had a vertical asymptote. And if you have a vertical asymptote, this is a non-removable discontinuity. You might even run into some piecewise functions. So if you are told that f of x is x plus 2 for x is less than or equal to 1, or x when x is greater than 1, think about your limits. Limit as x goes to 1 from the left side of the piecewise function being x plus 2, your answer is 3. But if you take the limit as x goes to 1 from the right of x, you get 1. So the limit from the left does not equal the limit from the right, therefore you have a jump discontinuity. So now let's use some of these ideas to answer various questions. For example 4, I'm approaching C from the right-hand side. In each one of these questions, C's been defined. C from the right-hand side of 2, okay, so this is a nice smooth polynomial. My answer is -2. C from the left-hand side of 2 is -2 as well. I love a good polynomial. So then we get the function is, as x approaches c, is going to be -2. So that becomes a very nice little problem. This graph is a continuous graph because it has no discontinuities. Ooh, fancy. All right, now for example 5, if I take the limit as x approaches c, this case c is -3, from the right, the answer is 3. Now from the left, the answer is 3, which is great. But the function, as you can see, the function limit as x goes to c is going to be 3. Now I do want you to note here that your domain is going from -infinity to infinity, because even though it has a hole in it, it does jump up, so that's fine. This is a removable discontinuity because you could plug in the hole if you needed to. The limit from the left equals the limit from the right, but it is not continuous because the limit is not equal to the function evaluated at -3. Now for example 6, okay, you can see a lot's going on here at example 6. The limit as we approach c from the right is going to be equal to your y value, that's your 0. C from the left is your y value, once again, that is 2. So the limit as x approaches c for f of x does not exist, and you have a jump discontinuity. Not only that, but your function is not continuous. So we discussed just a tiny bit about continuity. The definition, though, of function f is continuous at c when 3 conditions are met. The function at c is defined. The limit exists, so that means the left side is equal to the right side. And this last part, the limit as x approaches c of f of x equals f of x. The function is continuous on an open interval when the function is continuous at each point on the interval. So a function is continuous on -infinity to infinity if it is continuous everywhere. Now, just a reminder, the existence of a limit. The limit from the left has to equal the limit from the right, but to be continuous, let's sum it up. The limit as x approaches c from the left of the function has to equal the limit as x approaches c from the right of the function has to equal the function at c. All 3 of these pieces must work in order for the function to be continuous. Whew, it sounds like this is such a serious topic, and it really is. Trying to figure out where your functions are continuous or not continuous is one of the key concepts that we want to study, especially focusing in on these one-sided limits. So I chose some special functions. We have our piecewise function and absolute value function, and this one called the step function. So the piecewise function, you're going to think about which piece to use. So for example, I'm looking for the limit as x approaches 4 from the left side. So 4 is a number bigger than 0. So I'm actually thinking about the limit as x approaches 4 from the left side of x minus 2. I try substitution, and I get 2. All right, didn't matter if it was from the left or the right side, though, did it? So the limit as x goes to 4 from the right side of x minus 2 is also 2. Now, since the left side and the right side of 4 give me the same answer, the limit as x approaches 4 is 2. Oh, look at this. H at 4. Let's see. Wait, it's still just going to be 4 minus 2, which is 2. So now this next question, is h of x continuous? Don't be fooled. It is continuous at 4, but the place where you might have trouble thinking about continuity is at 0, where the piecewise function connects. So I want to check, is the limit as x goes to 0 from the left side, which is your 1/2 x squared minus 4, well, that's -4, equal to the limit as x goes to 0 from the right side, which is x minus 2, which is -2. So is it continuous? The answer is no, because the left side does not equal the right side. And this discontinuity is a jump discontinuity. All right, your absolute value function. These are really kind of clever functions. So you can see that something strange is happening in your domain when x equals 1. If you make a table of values for this function, what will happen, let's see here, if we put in x is 2, make a little table, that'll make life easier. Here we have x, and we will have g of x. Pick numbers to the left of 1. Let's pick out -1, 0, negative, or 0.9, and 0.99. So if you pick out numbers to the left of 1, substitute them in, you get +2 over -2, you get -1. Put in 0, -1, +1 over -1 is -1. Wait, you're getting -1 for every answer to the left of 1. So let's put in 1, and the answer is -1. We have an open circle at 1 because of the domain restriction. Now, if I do the same thing, except put in numbers to the right of 1, here's my x, here's my g of x, numbers to the right of 1. Well, that would be 2, 1.9, 1.01. Now put in 2, you get 1 over 1. You get, all of these are 1 again. But open circle, because you're not allowed to touch x is 1. So you can see this absolute value function is very cleverly just two horizontal lines. So as we approach 1 from the left side, your answer is -1. As you approach 1 from the right side, your answer is +1. As you approach 1, your answer does not exist. G at 1 does not exist. Is this function continuous? No. And this, once again, is a jump discontinuity. Now, at the end of the lesson, I'm going to give you instructions on how to use your calculator for this question, so that will be optional. The last interesting function we have is called the step function, or the greatest integer function. Those of you who are into programming should love this function. It's also called the INT whenever you're using programming. Depends on which language you're in. All right, so what happens with this is you put a number in and it rounds down. It always rounds down for the greatest integer function. So if I put in -3, now remember I'm approaching from the left, approaching 3 from the left side. Think about numbers that approach 3 from the left side. So we have x's, we have s of x for our step function. Numbers to the left of 3, 2.9, 2.99. Remember, I want to get really close. Now, when you substitute 2.99 into the step function, you get 2 times 2.9. It rounds down, so that's 2 times 2, which is 4. Oh, wait a minute. All of these are going to be 4 because it always rounded down. So the left side is 4. Now, what if we're on the right side of 3? So we put in 3.01, 3.1, and 3. This will probably give us the idea. So when I put in 3.01, it rounds down to 3. That 3 times 2 is 6. 3.1 is rounded down to 3. We're getting 6s. So when I put 3 in, that's also 6. Okay, so 3 from the right is 6. So the limit as x approaches 3 does not exist, and s at 3 is 6. Is s of x continuous? No, of course not. Why do you think it's called the step function? The graph using the step function makes steps. So I'll also show you how to do that one on your calculator. So classify this continuity. This is a jump discontinuity again. And now it's time for you to practice. Notice I've written, please only practice for 20 minutes. Set a timer if you need to, but work on your one-sided limits. You have some jump discontinuities, and make certain that you follow all the directions. Find the interval for which the function is continuous, the values that make the discontinuities, and classify each discontinuity. Make certain that you've given these a try before you check through your answers. So as you look at number 12, notice that you need to use your limit notation to prove when your function is not continuous. Sometimes that limit notation will also help you figure out when you could force your function to be continuous. Question number 13, let's look at that one together. So we have a constant a such that the function is continuous over the entire real number line. We want to show a complete analysis to figure out what that a needs to be. In order to do that, first recognize that 3 is where the piecewise function is going to connect. We're going to find the limit as x goes to 3 from the left of our function, then the limit as x goes to 3 from the right of our function. When we're using the left-hand side, that's going to be ax plus 1. Substitute your 3 in, we get 3a plus 1. When we're on the right-hand side of the function, that's going to be ax squared minus 1. So that gives us 9a minus 1. Now, in order for this function to be equal to each other, we're going to figure out when does 3a plus 1 equal 9a minus 1, and that will give us negative 6a equals negative 2, or a equals positive 1/3. So in order for f of x to be continuous, your a value must equal positive 1/3. Now we're going to do something similar for for our second function. Notice that lovely sign of x over x. That's going to make things way more interesting. So we take the limit as x goes to 0 from the right-hand side of our function, and the right-hand side of the function is going to be a minus 2x. And then we'll find the limit as x goes to 0 from the left side of the function, and that's going to be your 4 sine x over x. Now the right-hand side of our function is going to be a when you try substitution. The left side of our function, we're using the concept that our sine of x over x will go to 1 as x approaches 0, so this equals 4. So in order for our function to be continuous, 4 must equal a. And in this case, we let a equal 4, and you will have a function that is continuous. In the last part of our lesson, we're now up to page 79. Work on multiples of 3. Now, I chose multiples of 3 because I don't think you need to work on 60 questions. If you want to do odds, that's fine with me. But do try to practice several of these questions. Also, 61 to 65 odd, and here we have some multiples of 3 again. Notice at the end I say consider questions 119 and 121. So if you are supercharged about thinking through some of these more complex problems, have I got some problems for you. Also notice at the bottom of your notes, I've told you how to access your absolute value from your calculator. Use math and ABS, and then put in whatever you need for x. And if you want to use your step function, it's the int function, put in the x as well. If you want to round up, that would be your int function of x, which rounds down. But you know what? Add 1, and now it's rounding up. Now, if you want to get super fancy and figure out multiples of 5, you could do int times 5 of x, and then all your answers will be multiples of 5. So that's just something for you to consider. Have a great day, and I'll see you during the next lesson.